this lecture, we're going to introduce two of the basic blackbody radiation laws. The first is going to be the Stephan-Boltzman law. So over here, we have the blackbody radiation distribution given by the Planck function for a variety of temperatures. And you'll notice that in each case, T1, T2, T3, T4, T1 being the greatest temperature, T4 being the least temperature, that the total amount of radiation, i.e. if you integrate underneath the curve, increases significantly as temperature goes up. And you'll also notice that the peak of the Planck radiation distribution function actually moves to shorter wavelengths as the temperature goes up as well. And the blackbody radiation laws that we're going to be deriving, or at least outlining how to derive, will essentially explain those two features of the observed Planck blackbody radiation distribution functions. So we know that we have this equation for the functional form, and the irradiance for a blackbody, and we're going to use the asterisks to essentially denote that we're talking about a blackbody, is equal to the integral of the irradiance of a given wavelength times the integral of all of those wavelengths going from a wavelength of 0 to an infinitely long wavelength. And the Stephan-Boltzman law indicates that that is equal to sigma t to the fourth, where sigma is the Stephan-Boltzman constant. And we have this equation that the irradiance is equal to epsilon sigma t to the fourth, where epsilon is the emissivity, and you'll notice that the asterisk is gone because this is appropriate for a gray body, which is an object that's not necessarily a perfect absorber or a perfect emitter. If it were a black body, then the emissivity would be equal to 1. For a gray body, the emissivity is going to be somewhere between 0 and 1. And so this is the formulation of the Stephan-Boltzman law, which essentially integrates the area underneath the curve. And you'll notice that the area, the energy associated with this goes up as temperature to the fourth power. So a doubling of the temperature of an object quadruples the amount of energy that is being emitted by that object in terms of radiation. So that's the Stephan-Boltzman law, controlling the entire amount of energy that's emitted by an object. And then we have Wien's displacement law, which essentially is trying to identify the wavelength of maximum emission. And so the way to do that is to take the derivative of the the Planck radiation distribution and set it equal to 0, and then solve for the wavelength of maximum emission. And if you do that, taking some mathematical simplifications along the way, we actually do that as part of a homework problem. You'll end up with the wavelength of maximum emission is equal to a constant, in this case 2897, divided by temperature, where temperature is in degrees Kelvin, and the wavelength of maximum emission, if you use this particular constant, will be in units of micrometers. So if you can imagine an object that's a temperature of 289.7 Kelvin, then you would end up with a wavelength of maximum emission at 10 micrometers, which is in the infrared. So this essentially describes how the hotter objects, the wavelength of maximum emission changes towards shorter wavelengths. Higher temperature, shorter wavelength.